Okay, now we're on problem 4. And problem 4 says we have a 3 microcoulomb point charge. So I'm going to call that little q. Is placed in an external electric field of magnitude. So I already have an existing field of 1.6 times 10 to the 4th newtons per coulomb. At what distance from the charge is the net electric field going to be 0? Okay, so this was a little confusing when I first looked at it, but it really makes a lot of sense if you think about it. The external field already existed, the E field already existed. So I'm just going to make some random decision to point it like that. Now I'm going to take this little tiny charge and place it in there, and if I want the net field to be 0, then the little tiny charge has to generate a field that's equal but opposite. Okay, so that leaves E equals KQ over R squared. And my little tiny charge is going to say that it's going to generate a field that's the same exact size as the existing one. When I'm some distance r away. So when I did that, I got r to be the square root of, okay, so I have this times this, which gives me 27 times 10 to the 3rd Newton meter squared over Coulomb. And I'm going to divide it by 1.6 times 10 to the 4th newtons per Coulomb. So I'm going to take the square root of that division, basically. And when I did that, I said, well, I have to have my little tiny charge 1.3 meters away from my existing electrical field. All right, let's go to number 5. Okay, on number 5, it says 2 charges are located on the x-axis, and then some are on the y, and we want to find the net electric field at the origin. So we have a lot of algebra, but your teacher's pretty nice to you, because if you look at this setup, this is a positive 6 microcoulombs. This is a positive 6 microcoulombs. Then I have this one up here. That's a negative 8 microcoulombs. And this one here, that's a plus 3 microcoulombs. And then I have some distances. So this is going to be my origin right here. And I'm going to make that be a different color. This is going to be my origin right here. So right there, I want to know what is E right there. Okay, I'm going to call this one Q1, Q2, Q3, and Q4. And I know that this is 4 centimeters in that direction, and 4 centimeters in that direction. And then this is 5 centimeters. And then that other charge, the 4th charge, is located at X is 7 centimeters, so 2 more centimeters up here. Okay, so I'm going to look at electric fields. I know the electric fields go away from positive charges, so I'll have one here, that's E1, and that's E2. And you can see immediately they're the same size charges, it's the same distance, so E1 is going to be canceled E2, or E2 cancel, E1 equals cancels E2, or E2 cancels E1. Alright, so then these are really the only ones I have to worry about. So Q3 generates an electric field in that direction because it's going away from the positive charge. Q4 generates an electric field in that direction because it's going toward. So I just need to worry about E3 and E4. So E3 is going to be K Q3, which is 3 microcoulombs, over 0.05 meters squared. Don't forget to square it. So when I did that, I got E3 to be 1.08 times 10 to the 7th newtons per coulomb, and it's directed downward. Then I did the same thing with E4. So I said, well, E4 is going to be 9 times 10 to the 9th Newton meter squared over Coulomb squared times 8 microcoulombs all over 0.07 meters squared. So E4 is going to be 1.47 times 10 to the 7th newtons per coulomb, and it's going to be headed upward. See it right there toward the negative. So the E at the origin is going to be a positive 1.47 times 10 to the 7th newtons per coulomb with a negative or minus 1.08 times 10 to the 7th newtons per coulomb. So when I did that, I got 3.9 times 10 to the 6th newtons per coulomb. And I said it had to be pointing in that direction because that was the direction of the larger electric field. So there's number 5. Let's take a look at number 6. Number 6 said, a small drop of water is suspended. Okay, well that means that gravity's pulling down. So there must be some force pushing up on it. It's the electric force. Now it's in a field that is pointed upward. So if the field is pointed upward, then electric fields go away from positives and toward negatives. So if there's negatives up here and this thing is being pulled toward the negatives, that tells me this must be a positive charge. Okay? So I know it's positive. And then my explanation would be an electric force Okay, so an electric force is acting upward on the water to balance gravity, pulling down on the gravity. Would help if I could spell. Pulling down. If the E field is upward, then negative charges must be above the droplet. How do I know? Because electric fields go away from positives and toward negatives. This means my droplet is attracted to the negative particles. Okay. Part B says, well, how many protons, excess electrons or protons reside on the droplet? So I said, well, mg equals electric force. So mg equals EQ. So mg divided by E will give me Q. So they gave me the mass is 3.50 times 10 to the negative 9th kilograms. Gravity is 9.8. I want to divide that by E, and they told me the electric field was 8,480 newtons per coulomb. So I got Q. And when I did that, I got Q to be 4.045 times 10 to the minus 12 coulombs. And so now I want to set that value. And I know that one proton has a charge of 1.6 times 10 to the minus 19 coulombs. So the number of protons that I got was 2.5 times 10 to the 7th coulombs. All right, let's move on. Number 7. Number 7 said a proton is moving parallel to a uniform electric field. The electric field accelerates the proton and increases its linear momentum. So MV final is 5 times 10 to the minus 23rd kilogram meters per second. MV initial is 1.5 times 10 to the minus 23rd kilogram meters per second. Delta MV is going to be the difference between those two, which is 3.5 times 10 to the minus 23rd kilogram meters per second. And they want to know how it took 6.3 times 10 to the minus 3rd seconds to do that, and they want to know how big is the electric field. Well, I have to get E is equal to F over Q. So first thing I want to do is get F. Well, I taught you a long time ago that F delta T equals M delta V. So F is going to be equal to the change in momentum over the change in time. Change in momentum was 3.5 times 10 to the minus 23rd. Kilogram meters per second. Time that it took was 6.3 times 10 to the minus 3 seconds. So I solved for my force, and I got 5.56 times 10 to the minus 21 newtons. So there's my force. Now they want E. Well, E is F over Q. So I'm going to take that 5.56 times 10 to the minus 21 newtons over the charge of a proton, 1.6 times 10 to the negative 19th coulombs. And my E is 34.7 newtons per coulomb.